Today we're going to finish off our last problem, which is question 4, propagating uncertainty, calculating total uncertainty, and we're back to our propane tanks. So still can't get these propane tanks out of my head. I can't use mechanics to solve this problem yet until we basically look at lecture 8, but until then we could at least calculate some total uncertainty. So my propane tank is cylindrical with a length of 54 inches and a diameter of 30 inches. So this is my propane tank. So my length, cylindrical, so I have length, I have some diameter here. So I know if that's the case, then I know that my volume is going to be equal to pi times r squared, or d over 2 squared times L. So my volume is going to be a function of d and L. 1 inch equals 0.0254 meters. You don't need that. I'm sure you all have memorized that. I measure these dimensions with a ruler with centimeter tick marks. So there's going to be some uncertainty of L, which is equal to 0.01 meters. There's going to be some uncertainty of D, 0.1 meters. That's going to be a bias uncertainty, so keep that in mind. Trying to measure the pressure in my tank. So our fundamental expression is going to be this. Pressure is going to be a function, it's going to be nRT over V. So pressure, we're going to plug in this equation for volume. So pressure is going to be a function of N, R, T, D, and L. So P's pressure, exactly, this is going to be a gas constant. We're going to probably assume no pressure there, but let's keep reading. Measure the pressure in my tank using my tire pressure gauge. So below are various measurements that I made. The number of moles of gas should nominally be 10. So N is equal to 10 moles on average. Again, this is like our X bar N. And the manufacturer had the gas has a resolution of 0.1 moles. So there's some uncertainty in N equal to 0.1 moles. I utilize a glass thermometer with degree interval markings for temperature. So our temperature is going to have some uncertainty and some temperature, which is going to be equal to a degree intervals. So 1 degree K in this situation. So that's the uncertainty in temperature. So you utilize a glass thermometer, and then you could be basically uncertainty in degrees C too, but it'll be, again, we know that to get to degree K, we're just going to take degree C plus 273. So if there's an uncertainty of 1 degree C, it's equivalent to uncertainty of 1 degree K. Anyways, so that's it. So now we are asked, draw the generalized block diagram for measuring pressure with my tire pressure gauge. You do not have to do this in this course because we did not cover that generalized. Basically, you don't have to do that indirect measurement process because we did not cover that in class. But you basically have a tire pressure gauge. It has a cylinder and there's like a spring. So I'll do it for you. So our measure end, we're trying to find pressure. You can calibrate this basically with a known tire pressure that you can know. So we're going to convert pressure. It's going to fill basically some volume here. So pressure, that tire pressure is going to be fill this volume, and there's going to be a spring in here too. So volume, and then we convert that spring. There's going to be some, you could kind of use the force of a spring. Hooke's law minus kx. So that could be your sensor transducer step. But anyways, we're going to measure the displacement of that spring. So that volume is going to push on that piston. So it's going to convert, this pressure is going to be converted to force. That force is going to push and cause some displacement. So that's the transducing step. You could use this to kind of look at the displacement, and your readout is just going to be like, it's a manual, it's not a digital. So it's just this stick that pops out. And then you measure with those tick marks. Anyways, you will not have to do this for your exam, but you will have to be able to answer this question like this. Calculate the total uncertainty and pressure. What contributes most to uncertainty? So let's go ahead and get started with that calculation. So I'm going to delete everything from my, actually I'm just going to make a new note. But I'm going to be safe, and I am going to clear my kernel. Quit kernel. I would consider doing this between every problem. So our fundamental equation, so actually let's define some values here first. So my volume, V equals basically pi times L times d divided by 2, so squared. So let's double check that. Let's just kind of record some values here. So I know my uncertainty, I know those things here, I know my pressure is equal to N times R times T divided by V. So that's just going to be that right there, nRT divided by V. So now we have pressure as a function of N, R, T, L, and D, just like we wrote there. There is no statement talking about any uncertainty in R, so we don't have to take that partial because uncertainty in our gas constant is going to be 0. Now there is some uncertainty that we see, obviously, with our N, T, diameter and length as well. So we'll have to take those partials. But first things first, it says here, rules of gas should be nominally 10, manufacturer this, measured kind of these markings, etc., etc. There's the dimensions. But we're also given a list of data sets. So we need to figure out the precision error here first. So there's precision error because we have a list. So let's go ahead and calculate that out right now. So let's call this my XD, X bar D. It's going to be the mean of this list, 0.7, 0.8, 0.76, 0.81, 0.76, 0.6, 0.7. So I'm going to do also the standard deviation of this list. So SD, my diameter, so I'm going to do standard deviation. Great. And then I'm also going to do now the same thing for length. So I'm just going to change these values here. We're going to need these later. So XL, SL, and then we're going to do the same thing for temperature. ST, ST. Let's do L first. Luckily, these are all in meters. Be careful with units. You never know what I might do. 1.28, 1.21, 1.37, 1.4, 1.25. Right, take this list, copy it, paste it. Let's do the temperature. So we got 300, 299, 305, 300, 307. Hopefully I don't make a mistake on here. 295, 301. Let's do that numerically. Let's double check our answers here. So 15. Let's look and make sure that we are. Oops, not 395, 295. That is a big mistake. So 301, that looks pretty good. Let's just double check here. Let's do that numerically. So that's the standard deviation of our temperature. Excellent. 1.304, that looks pretty good. And all right, so we've got our basically the ingredients we need for our precision error. So this problem asks us for at a 95% confidence interval. So let's go ahead and find out these values. So luckily it's all these have the same length. So 1, 2, 3, 4, 5, 6, 7 measurements. So my T of 95, so it's 5% out of an alpha, TO25, nu of 1, 2, 3, 4, 5, 6, 7, a nu of 6. Let's go ahead and look that up. TO25, nu of 6 is going to be 2.477. So let's double check that right here. 2.477. Excellent. So let's go ahead and write that down. 2.447. So now I can figure out my precision error. So my P in my first P in my diameter is going to be T025 nu times nu 6 times my S of D divided by square root of the number of samples. It's going to be 7. Square root of 7. That. I'm going to divide out by the nominal value. So that's going to be that precision error divided by Actually, we'll do that in just a bit. Actually, we'll divide that right now. Divided by my x of d, x bar d. Now I'm going to do the same thing for values here, here. So this is for my values of length. Still the same value here, length, XL. And then for temperature, these are the normalized values. So this is in a fraction. So TO25, new, standard deviation, divided by that, divided by XT. XT, ST, and that's it. That's what we've got. So these are all in fractions now. We'll work with those in percents later. So now we have to go and do our partial derivatives. So I need to do my bias error calculation. So bias in P is going to be equal to, so I need to take the partials. Let's go ahead and set this problem back up. So I need to take the partial of P, my pressure function. So I'm going to do dP dN equals derivative of pressure with respect to N. I'm going to do my dP dt. So I'll keep it lowercase. D pressure with respect to T. Oh, excuse me, not T. Capital T. Here, dP dd equals the derivative of pressure with respect to D, and dP dL, which equals dP dL, is the derivative of pressure with respect to L. So I have all my partial derivatives there. So now let's set up my equation. So it's going to be, I'm going to normalize this, so square root of dP dN times uncertainty in N divided by pressure squared, because again I just want this as a kind of fraction here, and I'm just going to calculate the whole thing. So here dP dt times the uncertainty in P, T, excuse me, dP dt divided by pressure plus, same thing here. Now I need it to with respect to D, uncertainty in D, plus, place that in, dP dL, uncertainty in L, right here, square root, and that's it. So this is normalized, so now I just need to look at BP slash dot. So what is my D is going to go to my XD, or actually my diameter. So actually let's look at their X bar D. So that's going to be my X bar D. My uncertainty, or my length, is going to go to my XL. My T, my thickness, or my, excuse me, my temperature, T is going to go to XT. And then my, I think that's it. My N is going to be, how many number of moles should I be? Should be nominally 10 moles. This has a resolution there. So now I need to look at uncertainty. So my uncertainty in D is going to be what? It's that centimeter tick marks. So it's going to be 0.01. My uncertainty in length is going to be 0.01 meters. My uncertainty number of my moles, it has that resolution of 0.1. So uncertainty in N goes to 0.1. And my uncertainty in temperature is going to be a degree. So uncertainty in T goes to 1. And here, it's the uncertainty there, and we can now plug and chug, and we get this value. So this is, again, not in percentage yet, we're just in pure fractions, so my total uncertainty U of P is going to be equal to P equals my square root of this, my bias pressure, my BP, and that's going to be squared, plus my precision air. Let's actually go up here and see how I find it. Precision air in D squared, plus my precision air in L squared, plus my precision air in temperature squared. And then I'm going to substitute in for all of these good values right here. And I'll get my expression. So multiply this by 100, because again, this is still a fraction. So total uncertainty is about 10%. 3% of that is due to bias error. And we could look up here. 4% of that is due, and almost actually 9%. So the largest uncertainty, which you can see here, is actually that precision. So about 9%, 9% before we kind of sum it all together. So that is the full solution. So we could see and make kind of some adjustments. Unfortunately, again, with precision air, you just have to hopefully maybe buy a better, get a manufacturer of a better pressure vessel, and then hopefully there's some less uncertainty in kind of the distribution of those diameters. But yeah, that's about it. So that is all exam 1. So if you're comfortable with that and you feel like you could do that within 90 minutes and submit within 10 minutes, you're going to ace this exam. So good luck with studying. If you have any questions, be sure to come to the review session and then email me afterwards if there's any other lingering doubts or questions that you have. So good luck, and I'll see you all on Monday at 9:30. Thanks. Have a good one. Bye.